Good morning. My name is Reid Hislop, and I'm the product manager for our Advanced Composite business here at Trelleborg. Speaking to you today from our Innovation Center here in Stuttgart. Thank you for attending globally. What exactly do we mean by advanced composites, and how is it different than conventional composites? Today, we will answer that question, review our manufacturing process, and then talk to you specifically about some market examples where our products are being used today. But first, let's take a quick look at our agenda. There's some key principles as it relates to our manufacturing process that I want to be able to discuss. Those include unidirectional fiber alignment, something that we call automated fiber alignment or AFP, and in-situ consolidation. But I want to be able to make sure I'm spending the bulk of our time looking at customer use cases. And of course, I'll go ahead and take some questions via chat towards the end of my presentation. So feel free to put those questions into chat at any time on any slide, and hopefully I can get to those before we wrap up today. So what are we talking about exactly when we say advanced composites? Well, here's a picture of some of our thermoplastic composite parts that we make on a daily basis. These primarily all have a unique function and mechanical properties that they deliver. Generally, they are lightweight and high strength. They offer a broad selection of material availability, including carbon fiber PEEK is what we mostly work in, but there's also glass. And it's really about consistent and repeatable manufacturing. So what I'd ask you to do is keep these principles in mind as we review some of these use cases. But first, let's take a quick introduction overall at our technology. So Trelleborg Sealing Solutions Albany, as we're known, is started out as an incubator program out of a local technical university with the intent of using thermoplastics and unidirectional fibers to create new, durable, and lightweight structures. So we start with pre-preg materials. You can see those here in the photo in the middle. On top is a spool of what we call pre-preg tape. This looks like 1-inch tape. These are made by leading pre-preg manufacturing companies like Solvay, Supreme, and others. So we start our overall process with these high-grade composite materials. There's a combination of both fibers in these and a polymer, and you'll learn a little bit more about that as I continue. Some of our certifications are over here. I think AS 9100 is actually at D or E level now, changes on an annual basis. You can see some of the industries that we're involved in here. We really started out as an aerospace vendor or as an aerospace supplier, but you can see that we've migrated a lot of our technology and our composite parts to other industries. And again, here's a quick overview of some sample materials that we use and that we process. So when I mention processing, what am I referring to? Hopefully you can see this multi-axis robot here. This is actually one of our work cells. You'll see on the top our pre-preg materials that are in a variety of different spools up here on top. Those spools feed tape into the processing head. And that processing head provides a combination of time within which it's laying down pre-preg materials, temperature, which is at the material's melt point, and compaction to produce a fully consolidated part. So there's no post-processing required. In other words, there's no autoclave process, which is a must within thermal set manufacturing. So without this post-process, we call this in-situ consolidation. So basically, we develop these new parts, if you will, kind of on the fly. They're on a tool. When they're completed, the material is allowed to cool. The tool is removed, and that part is ready for production. So why is fiber alignment so important? Well, we're going to take a bit of a close-up view of this, if you will. So I mentioned the resin or the polymer that's available. And the pre-preg tapes that we get from these manufacturers are about 40% volume resin and 60% fiber. So those are probably some of the top specifics in terms of a balance there between resin and fiber that you can get in the industry. The micrograph shows uniformity in fiber distribution. So this is fully immersed in thermoplastic resins. The fibers provide the strength, of course, and the resins transfer that load across the part. So that's why the unidirectional compared to chopped fiber is so important for us. Some fibers may have more or less thermoplastic resin, depending upon the application. But what we end up with here is strength and stiffness in one direction. So we use that understanding of strength and stiffness in one direction to make our parts. So we have the ability to be able to wind at a variety of different angles. So knowing that those carbon fibers or fibers generally are strong in one direction, we use that to build our parts. So now that you know a little bit more about what we do, let's look further at the process. So I mentioned, time, temperature, and compaction. So this is a little bit of information related to in-situ consolidation, or heating, quite simply as it's known. Over here on the left-hand side, you'll see a hot gas torch. Here, this is a legacy process. So you can see where the incoming tape is drawn in to the process. That tape is then heated by hot gas, or in most cases now today, laser. There's a plume of nitrogen energy, a nitrogen gas here that we're heating with the hot gas torch. So not only are we heating the incoming tape, but we're also bringing up the previous ply up to its melt temperature as well. And in doing so, we can provide a compaction force here and basically melt bond this incoming tape with the prior substrate. So depending upon the complexity of the tool, we're able to manufacture net new parts in this regard. So I mentioned the laser is a very similar process. It's new or newer for us. Laser allows us to be much more energy efficient. So we can basically move more quickly with a laser heating system, which is important to any of our production customers. But, hey, enough about our overall process. Let's look at some examples here. So what I want to be able to follow here are case studies with, problem, resolution, and outcome. So let's take a look. I think I have a couple of energy examples in here. Most of the products we've shown here have been made from carbon fibers, which appear as black. But when you switch to glass fiber, we end up with an electrical insulator, which is interesting. These parts are then widely used in industry, and specifically the oil and gas markets, to transfer high loads while providing insulation between electrical components. These parts are made from glass fiber PEEK, which provides high temperature and chemical resistivity, often seen in these industries. These parts provide excellent signal transparency for logging sleeves, often seen in the oil and gas industry again. As seen in the photos here, you see geometries can change from simple cylinders that we have here to more complex one. This is an octacylinder. So depending upon what the application is, we have the ability to wind on a wide variety of different shapes. You can see some machining characteristics have occurred on these in order to provide a higher tolerance fit. So these thermoplastic components are fully machinable post-production. Let's take another look at another energy example. These are drillable bridge plugs used for some zone isolation in a production well. Metals just don't do well on this type of harsh or wet environment. So what's the recommendation? Well, composite drillable bridge plugs. And a couple things I want to be able to draw your attention to here. One is that these bridge plugs here are actually bonded to a brass core. So there is the capability for us to be able to bond our materials, glass, carbon, etc., onto a metal core. But I'll draw your attention to the machining here in the photo in the upper left as well. So these are actually threaded bridge plugs, and so that capability can occur as well. You need a degree of expertise when you're machining these thermoplastic composites, but that expertise is wide known within the Trelleborg family or outside vendors. So what ends up happening is these become much easier to mill out these materials while still maintaining structural integrity. The result ends up being less downtime when using metals. So let's move on to a couple of aero examples. So this is an enclosure for sensitive electronics. Manufacturing enclosures for batteries or other sensitive electronics see a wide range of benefits from using thermoplastic composites, such as durability, protection as a metallic solution, as good as a metallic solution, while reducing nearly 70% of the weight. And we know how important that is. Being a thermoplastic, the enclosures are resistant to chemical and fluids and are also recyclable, unlike other thermoset competitors. But using our automated fiber process, there's flexibility in the geometry, as you can see here by the photos I've included, as well as allowing scalable manufacturing for large quantities. Again, there's no post-cure process with these because they're thermoplastics, they're cured on the fly. And we'll discuss that in a couple of examples coming up. But what you get is a carbon fiber peak structure, high strength to weight ratio, high stiffness to weight ratio, with a 70% overall weight savings. So really remarkable and quite impressive for those on the aerospace side. So this topic in particular is one that there's a lot of people in the company that are very excited about at the moment. This is a tension overwinding of a permanent magnet motor. So as we look at what's going on in the electrification of the automotive space with electric vehicles, this is becoming a very hot commodity across our business. So the applications include here microturbine generators, high-speed blowers, electric motors of any kind, including high propulsion aircraft. Energy storage is another place where these overwinds are used. What ends up happening is we place and consolidate the thermoplastic materials directly onto the magnet rotor assembly. These composites act as a retaining sleeve to hold the magnets in place when they're spun at high RPMs. The incumbent materials that we see today are metallic or thermoset, and they are manufactured as sleeves that must be press fit onto the rotor assembly. Well, many of you know that carbon fiber and glass fibers really don't like to be stretched. So the press fitting option is difficult, challenging, and can be time consuming. It ends up adding some uncertainty to the assembly process. Whereas with thermoplastic material and AFP, you can eliminate that whole assembly process and place the material directly onto the magnets. As well, an additional benefit is limited eddy current loss with a near hoop. Hoop wound is basically a 90-degree wind of the prepreg material. The use of non-conductive materials can be used to provide an insular layer, axial reinforcement to increase overall stiffness, and incredibly light compared to steel and other metallic components. So again, I want you to be thinking about electric vehicles here. The automated fiber placement process can induce a pre-stress in the material as well prior to placing onto the magnets, up to 1,000 pounds of tension to increase high radial compression on the magnet assembly. These can be chilled as well during manufacturing to induce further radial compression. So what we end up here with is that electric motor is being able to allow to operate at its highest demand. So there's some increased interest here regarding these electric motors by themselves. So very, very important application for us at the moment. Happy to chat further with you as we move along. So what about bearings? Bearings is an important application for us in the pump and compressor market at the moment. We make wear rings for the pump industry. We've been doing this now for 2 decades. We've always sold them through distribution. So now you can buy these directly from Trelleborg. So we were able to launch our bearing here in the European market in August at ACHEMA. Those of you that were there at ACHEMA, hopefully we had a chance to tell you a little bit more about the bearing. Our applications today are really fit in the petrochemical space. Plain, you can think about plain pump bearings. And of course, in the wider oil and gas industry, swivel joint backup rings. There's no galling or seizing in running in dry conditions, which you'll see a lot of in metal. So the resolution is improving reliability and more efficient pump operation. So in using composites, you exactly get that, ends up with better performance and less downtime. So that's critical for any of these folks that are operating these pumps on a high demand basis. So in addition to that, the advanced composite bearing, we have the high mod advanced composite bearing plus, which is basically adding a lower friction liner both to the ID as well as the OD in the bearings. So what ends up happening here is we basically have half the coefficient of friction versus our standard ACB, which you saw in the last slide, at the same time maintaining high stiffness. So this will not Caesar gall. It can see a continuous surface temperature of 274 degrees Celsius, allows a very tight tolerance with mating components, nearly zero CTE with traditional layup, high chemical resistivity with the continuous carbon fiber peak, and near zero overall moisture absorption. So we're extremely excited about both the ACB and ACB Plus for the bearing market, and there's some additional markets that we are looking at exploiting that technology as well. And so look for more information on that as we move forward. So this is all about anti-extrusion springs. So these are involved in subsea, very deep water pumps. So these pumps traditionally have seals in them that are made out of metal. So under pressure, those seals or that rubber compound may void, and what ends up happening is the metal springs damage the liner, which leads to a very quick failure. So being at the bottom of the ocean, you can't really afford to have failure. So the resolution was to replace metal with composites. So there's no damage, there's no corrosion. And of course, we end up with much longer life in subsea applications. So moving on to a biopharma application here, making chromatography columns for a customer here in the US. This is really made for new drug discovery. And if you think about the COVID vaccines, there was incredibly high demand for these because the problem is that acrylic and stainless steel chromatography columns are heavy and expensive. So we've been able to optimize with this customer a much thinner wall. It's about 4 or 5 millimeters. It's optimized for manufacturing and it's recyclable. So what ends up happening is there's more rapid new drug development. And again, with COVID and the resulting vaccine development, we just could not simply make these fast enough for our customer. So again, very exciting use of thermoplastic technology. These happen to be made out of glass polypropylene, but it's a very unique application for us. We have a lot of development experience here with thermoplastic helicopter drive shafts. What's happening here is that most of the aluminum and titanium that exists in helicopter tail boom assembly today are being replaced with thermoplastic components. The thermoplastic is lighter, of course, and is more damage tolerant than titanium or aluminum. We've got a number of different programs underway at the moment to look at the overall replacement here of these drive shafts. This lower photo here is actually a carbon fiber peak, but the subsequent outer layer on the OD is wrapped in glass just to help reduce overall expense. So with all of this, how can composites be used within your organization? So a couple of key points to consider. What is it about your existing materials that aren't getting the job done? What are some other options that you consider or could be considering? What should I be thinking about in terms of overall testing? Tensile strength, part simulation, in-service tests. These are all things that we take into consideration with our customers when they're looking at a composite solution. One of the first questions often asked is what materials? So I need you to think about 4 key considerations, operating temperature, mechanical loading, magnitude of the load, as well as direction, location, temperature, corresponding duration. What's the chemical exposure? And what are my price goals that I need to be able to meet if I'm looking at a composite solution for my business? So how do these items fit within my part and material portfolio? Those are those are some questions that you need to be thinking through, and all of us here at Trelleborg are happy to chat through those more specifically with you. Just in summary, the key takeaways for us is hopefully you'll see an overall increase in performance and efficiency through some of the use cases that I was able to talk about today. And I'm hoping that you can think about where you could be using this technology in your business. And again, the Trelleborg team is happy to chat with you about those specifically. Most of our customers come to us with a drawing of some kind or another. It's typically made out of metal of some sort, and that's an excellent starting point for us. So we can look at why that metal is maybe not doing the job, or maybe you need some reduced weight, or you need a more durable, chemically resistant solution. We're happy to chat with you about composites. So that's it for my prepared comments. I'm happy to open it up to questions you may all have. Just get to that here. All right. So feel free to add any comments that you have or any questions that you want me to spend a little bit more time on. I see a few of them coming in here. Please feel free to, again, type them into the chat. I talked a little bit about initial steps in evaluating the potential for composites in your business. Again, it's as easy as starting with a drawing of a particular part or component that you have some interest in making either lightweight or stronger or stiffer, or again, more chemically resistant. We're happy to chat through that drawing and what we might be able to do, and make a recommendation as to whether or not a thermoplastic composite solution would be advantageous to you. So advantages over other metal and other materials. The metal, I think, is fairly obvious. So lightweighting is a huge benefit associated there. So anywhere within your business where weight is a consideration, we'd like you to engage in looking at a composite solution. Is it possible to machine these composite parts once manufactured? Yes, absolutely. There is a degree of expertise required there, but it is fully machinable. We're happy to do that here on behalf of our customers. And of course, many of our customers do their own machining. So any other questions? Happy to answer those for you. But I'm encouraged by what we're seeing from Trelleborg in terms of new product development on the composite side. The bearings, the high mod bearings, is a perfect example of that. And what we're seeing here on the motor overwinds, as well as the stator sleeves within the automotive space, is terribly exciting and engaging for all of us. So those of you that maybe have that application, we're happy to chat with you, as we have a bit of a unique solution in that regard. And it's not easy, but our experience lends itself well to that. How is it possible to recycle PEEK with reinforced glass fiber? Yeah, that's a very good question. So we basically end up with chopped glass fiber. So it is impossible to create once again, a unidirectional fiber, because once those fibers are recycled, I think it's impossible to be able to create, once again, unidirection of those fibers. But there are some tremendous examples of where chopped fiber is used, and that's exactly where it would. So the resin, may be burned off as part of the overall process, while protecting the integrity overall of the fibers. And chopped fiber with a net new polymer is a perfect example of another life. Let's see. Are you able to manufacture parts by composite, like, for example, glass and carbon? Yes, and we do that almost at any given week. Our customers, depending upon what the application is and their demand and the mechanical properties that they want out of the part. As I said, on the drive shaft, you could see the final OD layer of the drive shaft was made from glass, I think S2 glass with PEEK. And it's just less expensive than carbon fiber PEEK. So that's typically the consideration. So again, depending upon the mechanical properties that you want to be able to get out of that part, we can use a combination of glass or carbon or any of the other materials that we process on a daily basis. So typical porosity level with AFP thermoplastic composites versus thermoset. I don't have any images that I can share with you in that regard, but it's typically porosity is in the range of 3 to 4% with our thermoplastic materials. I'm not quite sure how that compares to thermoset, but I believe thermoset could be in the 5 or 6% range. But if you'd like to reach out to me at reid.hislop@trelleborg.com, I'm happy to answer that more specifically for you. And again, happy to share some images with you.